Neurons are electrically excitable. That means they're capable of conducting an electrical signal from one end of the neuron to the other end of the neuron, which is a very rapid means of communication. However, in order to be able to conduct electricity, the neuron has to have something special called a resting membrane potential, which is a difference in charge between the inside of the cell and the outside of the cell. That's what that word means, actually, potential. Potential means there's a difference between one place and another, a difference between the inside of the cell and the outside of the cell, or a difference between the grade that you got on the exam and the grade that you should have gotten on the exam when your professor says to you, you had such potential. Anyway, let's talk about how the resting membrane potential is developed and maintained in the neuron. So here we have a neuron, except it doesn't have any of the fancy dendrites and axons because we don't need to draw those. And we're just going to look at two membrane proteins that are essential to create the resting membrane potential. The first of these is called the sodium pump. It uses a molecule of ATP, and for each molecule of ATP that it hydrolyzes or it breaks open to get the energy, it pumps 3 sodium ions from the inside of the cell to the outside of the cell, and 2 potassium ions from the outside of the cell to the inside of the cell. And it's the fact that these numbers are not the same that helps this pump to create the resting membrane potential. We'll talk about the potassium channel shortly. So let's say that we're starting off at the beginning of time. This cell has just been invented, and it has 100 sodium ions inside the cell and 100 potassium ions inside the cell. And it has the same thing on the outside of the cell. So there's no difference between the inside and the outside of the cell. And then we put this sodium pump in. Now, before we use the ATP for the sodium pump, let's tabulate some of our data here. On the inside of the cell, we have 100 sodium ions and 100 potassium ions. On the outside of the cell, we have 100 sodium and 100 potassium. What we want to do to see what the difference in charge is between the inside and the outside of the cell is not consider whether it's sodium or potassium, but to consider whether it's positive or negative. So let's add these up to get our total positive charges. Since they're both positive, 100 plus 100 is 200. And the total positive charges on the outside of the cell are also 200. Now, if we want to see if there's a difference in charge between the inside and the outside of the cell, we can take 200 minus 200, or the charges inside the cell minus the charges outside the cell. And there is no difference, so there is 0 resting membrane potential. Now, let's spin a molecule of ATP and see what happens to the membrane potential. So if we use 1 molecule of ATP, it's going to take 3 sodium ions from the inside of the cell and move them to the outside of the cell. So I'm going to take away 3 from this 100. And I'm going to add those 3 down here to the outside of the cell. Now let's do the same thing with potassium. Potassium, each time the sodium pump uses a molecule of ATP, 2 potassium ions are moved from the outside to the inside. So I'm going to add 2 potassiums here, and I'm going to take away 2 potassiums down here. And now I'm going to record the numbers over in the table. So now I have 102 potassium ions inside the cell and 98 potassiums outside the cell. I have 97 sodiums inside the cell, and I have 103 sodiums outside of the cell. So now let's figure out what our total positive charges are. 97 plus 102 gives us 199. 103 plus 98 gives us 201. 199 minus 201 gives us -2. So right now, after using 1 molecule of ATP, we've created a difference in charge between the inside and the outside of the cell, and we've begun to develop our resting membrane potential. Let's do it one more time with 1 more molecule of ATP. Just like before, we're going to take 3 sodiums away from the inside of the cell, so 97 minus 3 is 94. And we're going to add those to the outside of the cell, making that 106. And then we're going to take away 2 potassiums, from the inside of the cell, make that 96, and add them to the inside of the cell, which makes this 104. I hope I'm doing this right. Okay, so let's record the numbers in the table. This now goes up to 104. This goes down to 96. 97 minus 4 gives us 94. 103 plus 3 gives us 106. And now let's add up the total positive charges. 94 plus 104 equals 198. 106 plus 96 gives us 202. 198 minus 202 is -4. So the membrane potential just became more exaggerated. Now, let's take a look at what happens when the leaky potassium channel becomes involved. Actually, it stays involved. It's always leaky. It's always open just a little bit. And because potassium is concentrated inside the cell, has a higher concentration inside than outside, potassium is going to go through the channel from inside to outside, or from high concentration to low concentration. Now, let's say that channel is leaking, and in the time period that we're watching this cell, it leaks out 4 potassium ions. So I'm going to take away 4 from here, and no, I don't want to do that. Let's say that it leaks 2 potassium ions. All right, so I'm going to take away 2, and over here I'm going to add 2, so 96 becomes 98. And then I'm going to put the numbers over here, 102, 98. The potassium channel doesn't affect the sodium at all, so the sodium numbers will stay the same. That will be 94 and 106. And then we need to add the total positive charges. So 94 plus 102 gives us 196, and 106 plus 98 gives us, I'm so funny, 204. Am I doing that right, guys? 204? Yeah. All right. Now, if we subtract 204 from 196, then the difference is -10. Okay? So there's a big jump just by letting 2 potassium ions sneak back out. We get a big jump in the resting membrane potential. And I mention this because to most people, when you look at this, the fact that the cell puts energy into bringing potassium in and then just lets it leak back out seems like a waste of energy. But it's the movement of this potassium in a cycle that is actually creating the resting membrane potential, which allows the neuron to conduct its electrical signal from one end to the other.